All right, this is week number 3 of ERT107, the safety course. This week we are talking about safety circuits and introduction to some concepts with electrically controlled safety circuits and safety devices. So let's get rolling. So we're talking about that. There are lots of different manufacturers of safety control devices and products. Some of them listed here. Common ones you'll see in industry around here that we'll deal a lot with. Rockwell Automation, Allen Bradley. See a lot of that. SICK, you'll see a lot of. Siemens, another big one. Pills, you'll see them. STI for light curtains. Omron, see those devices around a lot, and all these other ones as well. Lots of different manufacturers that you'll encounter over your career, makers of safety devices. So what is this thing up here? If anyone can identify that, that is a PLC, or a programmable logic controller. We do 2 courses in our program dealing with programmable logic controllers. You're going to learn how to program those and control automation systems with them. So what are control systems? This is a control system is a device or a set of devices that manages, commands, directs, regulates behavior of other devices or systems. So basically this is the brains behind your automation system. So industrial control systems, we use these in industrial production for controlling equipment and machines. So basically if you have an assembly line or some type of automation equipment, this would be basically what controls that. You program it and you program it to do whatever functions you want it to do. A safety related control system, specific part of the control system, a machine that prevents hazardous condition from occurring. So this is our safety side of things. Can be separated into a dedicated system or could be integrated with the normal machine control. Some examples of this, typically the way things are done these days, safety PLCs, you're going to see a lot of that. You're actually going to learn how to program that in PLC Part 2. And then we have devices such as e-stops, light curtains, door sensors. We will get into what these devices do in the next 2 weeks or so. Safety-related control systems are designed to perform safety functions only. So what is the safety function? This is implemented by safety-related parts of the machine to control and maintain equipment under control in a safe state with respect to a specific hazard. So this is basically what protects you from hazards in these types of situations. Failure of a safety function can result in an immediate increase in the risks of the equipment. Safety function starts with a command and ends with the implementation. Overall safety that depends on the correct functioning of the process or equipment in response to its inputs. What is an input? Basically, this is our process that happens here. We have input devices. Inputs would be things like switches or buttons or things like that. That would be an input, anything that is a physical device in the field that we sense and give a signal back to our control system. We then process that information and we use that process to control outputs. Outputs being anything that our system is able to control. Things like motors, solenoid motions, so pneumatic or hydraulic motions, motors, things like that. So basically we have inputs, we have some type of control system, and we have outputs that are controlled. So let's get into an analogy here to try to figure out the different levels and strategies for trying to control something in a safe way. So let's step back for a second. Let's say that you have now you are locked into a action movie or horror movie, sci-fi movie, something like that. You were part of a team that has been trapped in some type of building. You're in the command center and you are being surrounded by whatever the enemy is. It could be aliens, zombies, terrorists, whatever this outside force is that is trying to come get you. Okay, so you are trying to be safe within your little command center there. Let's say there is one entrance to this building. It is about 500 meters away from where you are located. You need to know if there are enemies approaching that entrance. What kind of strategies would you use to be able to keep your team safe? So basically, you are in a building. You are over here. There's one entrance over here. This is a long ways away. How are you going to figure out if you are surrounded or there's things trying to get in through this door, like zombie invasion or something like that? How are some strategies you can figure out to do that? Let's think about this. So let's come up with, we're going to call this solution number 1. Simplest possible solution. Let's send one guard out there. Let's pick a member from your team. They're going to be they have guard duty. We're going to send out one single person, give them a radio. They're going to go stand guard. Their instructions are going to be, you're going to call back to the rest of us only if there is trouble. So basically, you guy over there, you go out to the guard post, take this radio, keep it off, turn it on, and call us if there's a problem. That would be one strategy. So let's think about the different possible things that could possibly go wrong with that strategy. So let's say that guard, along his way, he hears a noise and suddenly he is captured or killed or has his brains eaten or he's implanted with alien larvae or whatever that situation is. He's taken out. We never hear from him. Our instructions were call back if there is trouble. So if we don't hear anything, we assume everything is okay. In this case, we don't hear anything, so we assume everything is okay, but we're not okay. Alright, so that is a point of failure. Right there. Here's another thing. What if he sees something wrong and he tries to call back, he turns on his radio, and the radio doesn't work? Okay, that would be another point of failure. Okay. So that is two possible ways that this whole solution could fail on us. So this is a potential solution that could work, but it is not very good. Okay, so we'll call that solution number 1. What would be a better solution than that? All right, let's say we're going to do a similar thing. We're going to send out one guy, one single guard with radio. But this time we're going to tell him, take the radio, turn it on now, and keep on reporting in constantly to us as long as everything is okay. All right? So as long as everything is okay, you keep on talking to us, and then we know everything is fine. This way, if the radio suddenly goes silent, we can assume that something has gone wrong. Okay? So in this case, he gets captured or killed or whatever. This is going to result in no signal. We're going to know that that is trouble. We will interpret that correctly as trouble. If his radio were to fail, we will also interpret that as trouble. But in this case, this is the opposite situation we had before. Before, if the radio failed, we would interpret that as being okay. Now we will interpret that as being trouble, which is a better way to fail than the other situation. We call that being fail-safe. So we are failing in a safe way. Okay, that is a fail-safe condition. So we like this way better and for safety purposes. Here's the other thing. What happens if that guard gets captured and is cloned, and his clone actually maintains the radio signal? In this case, we don't know the difference. So the result would be a false OK signal, and our system has been defeated. So this is no good. Okay, so this is a better solution, but it's not perfect. Now let's look at solution number 3 here. In this one, we're going to send out 2 guards, both with radios. We're going to instruct them both to radio back constantly, and they're going to report back if everything is okay, assuming that no signal means that there is trouble. Also, if we ever get a case where one says everything is okay and one says there's trouble, we're going to assume that as trouble. If they ever disagree, so if they ever give us conflicting information, we're going to assume that that is a problem. Okay? So let's look at our situations here. Single guard gets captured. That's going to result in no signal from one guard. We'll interpret that correctly as trouble, so that's a good situation. Single radio fails, and guard is unable to signal a warning. We will also interpret that as trouble, and that is going to be a fail safe. So we will fail in the safe. It is an incorrect assumption, but we will assume that it is trouble. We will fail in the safe thing. So that is also good. If a guard is captured or cloned, and the clone maintains radio signal, the second guard is going to report something different. Okay, so then our signals are going to disagree. So this is the advantage of having redundancy or having two guards, is that we should be able to, if they only get one, if only one guard fails, our second one should still be okay and be able to report in the problem. And then in the event that both guards were to be disabled at the same time, or both their radios failed, this would actually be an extremely unlikely situation. And in terms of practicality of safety, the statistical chance of this happening is so minimal that we don't consider it to be viable. So we say that will statistically not happen. So we are okay with that. Now the one thing that could happen here is if both guards were captured and cloned, that could actually defeat our system. Okay, so that would be a problem there. So this is a pretty good solution. This is getting pretty close to perfect. The one thing we could do better here, two guards with radios. If we ever get signals that disagree, we know that one has been compromised. The last thing we're going to do is we're going to say the guards are going to use certain code words that they're going to use when they report back. We know that that cannot be copied by our enemies, so that we know if they ever get cloned, we can tell the difference. Okay? So we are good there, good there, good there, good there. And the final one here that we still had a problem with, if they're captured in clones, the clones won't know what those code words are, so we can detect that that is a problem. So this is the best solution we have so far. Okay? That is our solution number 4. This is the best situation we have so far. Okay? The only thing we could do that would be better is if we actually sent Chuck Norris out there as our guard. There is no possible chance of failure in this situation. This is our optimal solution. Okay, so how does any of that relate to our safety systems? Well, basically each of those situations kind of has an equivalent to what we deal with in an actual electrical safety system. Okay, so we're going to talk about normally open and normally closed switches or contacts. So a normally open, change colors here. Normally open is this guy here. We represent a relay contact like that, and normally closed we represent like this. Or on a push button, that's normally open push button. This is a normally closed push button. Normally open means that the contact is open or in a non-conductive state when the device operating it is de-energized or relaxed. So this basically means this only gives signal when I activate it or push it. Okay? Much like the guard that only signals in trouble when he actually sees trouble. Okay? The normally closed. A normally closed contact is a contact that basically works the opposite way. It's always giving signal when it's not activated. If you activate it, it actually shuts the signal off. So this is kind of like the person constantly on the radio, and they'll only stop being on the radio if they actually are disabled. Okay, so this is basically our normally closed contact. So example here, a normally open, we have voltage over here, we have our contact here, we have our light over here. This is a switch contact, a relay contact, a push button, different representations of this. That is the non-activated state, or if I trigger the thing, it actually closes, makes my light come on. Okay, so that is basically closing the circuit when the device is activated. This is normally open, so this actually requires activation to get signal. Now what I can't tell here, this requires my whole circuit to be good. If I break this circuit, like if I lose this wire here, or it becomes disconnected, or if my device doesn't work, much like the guy's radio not working, I can't tell that this is functioning. I can't tell the difference between this and activating and my wires are broken. Okay, I can't tell the difference between that, which is why we don't like normally open with safety circuits. Normally closed, on the other hand, this is the non-activated state, so it's always giving a signal. So if I was to, this is the OK condition basically, this is the activated or trouble condition here. So if I were to break this wire, my light would actually go off, which is the same as the activated condition. So this would be like the guy talking on the radio all the time, and if he sees trouble, he stops talking. Or if his radio goes dead because the batteries fail, he stops talking as well. We can't tell the difference between those two, but we're going to basically assume either one is a trouble condition. Okay, so that's normally closed. So that's why we would like that in a safety situation. So basically, normally open contacts on a safety device, it's like the guard calling only if there's trouble. Normally closed contacts, guard reporting all the time if okay. Okay, so that's the two circuits there. And like we said, with normally closed devices, even if that wire breaks, we can still tell that we will assume that this is okay, that this is a trouble condition on a broken wire, the same as if a device is activated. Okay, single channel versus dual channel. Pretty straightforward what they mean. Single channel, meaning one device with only one circuit through it. Dual channel, one device. So this is all one device here. But it's actually got two sets of contacts on it and two separate wires going through it. So two separate wires. So this is dual channel over here. This is single channel. And for obvious reasons, if this breaks, we don't know what's going on. Over here, if we get one wire that breaks, we still have one wire that works, and we get disagreement between our two signals now. And we know from our radio example, if we get disagreement between the two guards, we assume that is a failed condition, and we assume trouble. So here we have, again, dual channel. Like we said there, single channels like that single guard. Dual channel offers redundancy. It's like our two guard situation, so we like that better. And then monitoring of the devices, that is like using our code words. So monitoring allows us to actually check to see if on a monitored system we are able to check to see if there's an attempt being made to defeat the circuit. And we'll show a little bit of examples later on in the course of how you would do a monitoring circuit, but there are ways to tell if someone has tried to jump or out the circuit, and if it's still operating normally. You can do that with different types of monitoring. So that would kind of be like using those code words with the guard situation, because you can actually tell if someone is actively trying to defeat the system. And then the ultimate situation, the Chuck Norris of these situations, would be using a safety PLC with all two-channel, normally closed devices. That gives you freedom to solve pretty much any problem you want with a safety system. And that is the way most systems are done today. So common traits of safety signals: they should be normally closed. They should be used in pairs for redundancy. There should always be agreement between each of those signals when you're using a redundant pair. And if possible, there should be some form of monitoring or method of telling if something has been jumpered or defeated. Okay, so different devices we'll actually see in these circuits. The most common device we're going to see is a relay. A relay allows circuits to be switched by electrical equipment. It's basically an electrically operated switch, and it's used where it's necessary to control a circuit, and it's the basis of all industrial control. So basically in a relay we have an electromagnetic coil right here. Once that coil is energized, we create a magnetic field, and we physically move a mechanical contact, like you'd see going on over here. Electrical field generates magnetism, makes that metal contact move against a spring. So put power here, closes that circuit, light comes on. So what that basically allows us to do, it allows us to use one voltage to control other circuits of various voltages or multiple circuits. Relays can have many contacts to them. For example, this one here, we have one relay coil here, and then 1, 2, 3, 4, 5 separate circuits that this can control. 4 of them being normally open and 1 of them being normally closed. This is the normally closed one here. A contactor is basically like a large relay used for switching motor circuits. It's basically a large relay. It has a heavier spring and is rated to handle higher currents across the contacts. And then this is our basic safety circuit. So we'll learn how to draw this. This is a single channel circuit with no monitoring. So we have here a stop button, a start button, one relay, and the contacts of that relay are used here and here. So basically what happens here, if you push this start button, that closes this circuit. Closing that circuit now energizes here, because what will happen, I'm going to use my highlighter here, so we have power over here. That gives us power across here, which now energizes this relay. By energizing that relay, that now closes this relay contact as well, which gives us power across here. And now we've created a branch around this start button. We've also closed this relay, which now gives us power all the way to here, which now energizes this device as well. And when we do that, we can now remove power even after we release that start button. We still have power through this branch of the circuit. So even after we release this start button, we are still holding this circuit closed because of this contact here. The only thing that will break this is when we push the E-stop, and then when we push that E-stop, that will break this. We lose power all the way across here, which de-energizes this relay. Once that happens, then this opens up, drops power to this, and that equipment shuts down. So this is describing that function there. Now the problem with this circuit, this is a single channel control circuit. And it has a single point of failure. So there's several single points of failure on here. So if this e-stop were to fail in the closed position, so if this were to fail like that, then once we engage this circuit, there is no way to break it once that happens. Similarly, if this were to fail in the closed position, then once we engage this circuit, there is no way to break it and shut this. There is no way to shut this off afterwards. Or if this relay were to fail in the closed position, then this stays closed and this stays closed, and there is no way to break this circuit. So there's basically this has 3 points of failure. Sorry, not going to say 3 points of failure. Let's call it 3 points of single. So there's 3 different items here that could fail on their own and make this circuit not function in a safe way if they did. So because of this, this is a simple start-stop circuit, but it would not be considered safe at for a system that requires higher levels of safety. Okay, so to address these things later on, we're going to do this in the next lesson, we would have to add a couple things in there. We would have to add in some redundancy, some diversity, and we would have to add monitoring. And we'll talk about what those things are in the next lesson. Okay? So if you have any questions for that, we'll take those up on Friday. That is it for the lesson today, and we will continue on next in the class on Friday. Thank you.